Assalamu alaikum everyone. Chapter number 4. We are going to discuss all the cases of solving integral equation. So the example that we're going to solve is solve the following integral equation, discuss all cases. Y of x is f of x plus lambda integration from 0 to 1, 1 minus 3x of t, 3xt y of t dt. First of all, we know that this is a separable or degenerate kernel. So just separate the integral sign into this two parts. After splitting it into two parts, just observe it. If we have any variable other than t, take it out. After taking it out, take this complete integral as c1 and take the complete second integral as c2. Mark it as equation number 2 and mark this as equation number 1. After this, just write the c1 separately and c2 separately so we may know what is our c1 and what is the c2. Now consider the c1. Write c1 equals to integration from 0 to 1 y of t dt. Now we need the value of y of t here. So y of t will be f of t plus lambda c1 minus 3t lambda c2. I just plugged in the value here. After plugging in the value here, just integrate every term. Integrate f of t dt, integrate lambda c1 and integrate 3t lambda c2. We know that this is unknown right now, so we cannot integrate it. Just keep it as it is and apply the integration on these two terms and apply the limits of integration as well. After solving, we get this equation 3. Now we have to consider C2. After considering C2, we have to plug in the value of y of t again here. So let's plug in the value of y of t here. After plugging in the value of y of t, just integrate every term. And we know that we cannot integrate t f of t dt. So just take it aside and mark this complete equation as equation 4. After marking it as equation number 4, we are going to rewrite equation 3 and 4 as keep these two integrals on the right side and move all other terms on the left side. Combine c1 and c2. After rewriting equation 3 and 4, we got these two equations and we know that we can just solve this system of equation. Take this d of lambda, take this first column for coefficient of c1 and take the second column for the coefficient of c2. Just open this determinant. How we are going to open this? Multiply this main diagonal, then minus sign and multiply this second diagonal and simplify. Mark it as equation number 7. We will get a unique solution of the system 5 and 6 if this d of lambda is non-zero. So take this value as not equals to 0, simplify it. So it means we will get a unique solution if our lambda is not plus and minus 2. When d of lambda is not 0, c1 and c2 can be determined by solving 5 and 6. By putting the values of c1 and c2, so obtained in equation number 2. This was our main solution y of x. If I will plug in the value of c1 and c2 here, I will get my solution. The required unique solution of 1 can be obtained. Now, we have here f of x. That is unknown. We are going to discuss it right now. If f of x is 0, and lambda is plus and minus 2, then the solution is c1 equals to c2 is 0. If your f of x is 0, then your right side is going to be 0 here. And if c1 and c2, and if lambda is plus and minus 2 here, lambda is plus and minus 2 and f of x is 0, then from these two equations, we will get that c1 and c2 both are 0. So trivial solution exists. So lambda is plus minus 2 is the eigenvalue of the given problem. Now let's discuss these eigenvalues separately. When lambda is positive 2, if the lambda is positive 2, plug in here in these two equations, lambda is positive 2, I will get these two equations. You can see that the left sides are equal. These equations are incompatible. Why? Because left sides are equal, so if I equate them, this integral can never be equal to this integral. So this is incompatible equation. So they possess no solution. They can possess a solution unless and until they both are equal. So if we take them equal like this, or just move everything on the right side and make it equals to 0, then the possibility of solution can come. And we say that this is redundant and hence possess infinite many solutions. When lambda is minus 2, if I plug lambda is minus 2 in these two equations, I will get this system. Now left sides are equal, so again here they are not equal, the right side. So this is incompatible unless and until if they both are equal. So if we both take them both equal and just simplify them, if this condition satisfies, then we can get infinite many solutions, and this is again redundant. Now we are going to discuss the solution of equation number 1. This equation number 1, our main problem. First case, case 1, when your f of x is 0, then our equation is reduced to this one. Here f of x got 0. If lambda is plus and minus 2, equation 1 has trivial solution. And if lambda is not equals to plus and minus 2, then trivial. And if lambda is plus and minus 2, non-trivial solution, and eigenvalues are lambda is plus minus 2. To find the eigenfunction corresponding to these eigenvalues, we are going to use equation 8 and 9. This is for lambda is equals to 2, equation 8 and 9, with f of x as 0. If I mark f of x as 0, I will get here this equation equals to 0, this one as equals to 0, so I will get c1 is equals to 3c2. I will get c1 is equals to 3c2. So our equation, that is this one, y of x is f of x plus lambda c1 minus 3x lambda c2. F of x is 0, lambda is 2, and c1 is 3c2. Just plug in all the values here and I will get this equation. And we can take the constants as some other constant as a. So this is our eigenfunction corresponding to lambda is equals to 2. Now if I do it for lambda is equals to minus 2, put this in equation 10 and 11, simplify, we will get this c1 as c2. Put it in equation number 2, same as we did here. I will get y of x this. So eigenfunction corresponding to lambda is equals to this is lambda is equals to 2 and lambda is equals to minus 2 is 1 minus x and 1 minus 3x respectively. Now here comes case 2. For case 2, we are going to take f of x as non-zero. So equation 1 will be non-homogeneous and 3 cases will arise. First one, lambda is non-zero, possesses unique solution. If lambda is equals to 2, equation 8 and 9 shows that no solution exists unless f of x is orthogonal to 1 minus x. No solution exists unless your f of x is orthogonal to 1 minus x. Over this interval, that is unless f of x is orthogonal to the eigenfunction, we got this eigenfunction here, corresponding to lambda is equals to 2. When f of x satisfies this restriction, equation 8 and 9 are identical and these give us this one. They will become identical. Putting values of c1 in equation 2, your main equation 2 of y of x, I just plug in the value here, simplified, and I got this. Thus for lambda is equals to 2, I will see that this integral is 0, then equation 1 possesses infinite many solutions. Now come case 3, for lambda is minus 2, the same we did for case 2. Equation 11 and 12 shows that no solution exists unless f of x is orthogonal to 1 minus 3x, this one. Unless f of x is orthogonal to 1 minus 3x. Or unless, you can see that in this integral, unless f of x is orthogonal to the eigenfunction corresponding to lambda minus 2. When f of x satisfies this equation, equation 11 and 12 are identical and we will get this equation from 11 and 12. Putting value of c1 in your main equation 2, we'll get this equation. Just simplify it. After simplifying, Thus, if lambda is equals to minus 2 and this is 0, the equation 1 possesses infinite many solutions given by above equation. After discussing all these cases for this general equation, we will do in the next lecture the Fredholm alternative, and we will do an approximate method as well. I hope you understand this question. This question is very important as the paper point of view. This one that we discussed right now, that you have to solve the integral equation, you have to discuss all the cases. This question mostly comes in the exam, so you need to be careful while doing this question. So just do it again and again, have enough practice so that you may avoid any kind of mistake.